Here we go, solubility. We got the definition of solubility. We started talking about it up earlier with how a solution forms. With the salvation. You guys remember me doing that? Okay. So the definition of solubility. Solubility is an actual noun. It is a characteristic of a solute in a solution. So the solubility of a solute, the amount of solute that will dissolve in a specific solvent under given conditions of temperature and pressure. Okay, so sometimes, and you guys have probably experienced this before, that you can dissolve more stuff in warm solution than cold solution. Except, for example, if you ever try to make like hot cocoa and try to mix the hot cocoa mix into cold water, it doesn't work very well. You get the clumps of hot cocoa in your cold water in your dish. But when you heat up the water, it dissolves much more nicely. And so and yummy, and then you put the marshmallow in it, and it melts the marshmallow. All right, so that's the definition of solubility, and it's going to be a particular amount. It's going to be a particular amount of solute that will dissolve into a particular amount of solvent. All right, so let's turn the page here. So the nature of solute and solvent. 1. Likes dissolve likes. Similar things are going to dissolve similar things. Which means polar solvents are going to dissolve polar or ionic solutes. And non-polar solvents are going to dissolve non-polar solutes. Okay, for example, alcohol and water will dissolve in each other. Okay, but water and oil don't dissolve in each other because they're not like each other. It's the polar and non-polar thing. Okay, then we have the effects of temperature on solubility, and this is going to be the lab that we're going to do next week. Solids and liquids. When we are trying to dissolve a solid in a liquid, the solubility will increase with an increase in temperature. So in other words, the hotter the solvent, the more the solid is going to dissolve. However, for gases, it's not true, and you guys have experienced this. You guys ever had to open up a bottle of hot Coca-Cola? You take the bottle, a 2 liter bottle of soda, okay, and it's hot. What happens when you open the lid? You don't shake it up or nothing, but you open the lid and what happens to it? Okay, it spews everywhere. Right, that's. Well, if you shake it up and it's cold, yeah. But if it's cold and you just open it, it's not necessarily gonna do it. But if you just set it out in the sun and it gets hot, okay, then you open up the lid, it's all gonna spew out. Okay, this is because there's less gas that can dissolve in a hot liquid than in a cold liquid. It has to do with the motion of the particles. Okay, so gas and liquids, the solubility of the gas in the liquid will decrease with an increase in the temperature. Now, the solubility graphs, I've actually given you some solubility graphs on the back side of your homework packet, I think.
Yeah, you did.
Okay, this is the idea of what these are the idea of what we're talking about. It's I don't want to pull it. I don't have one pulled up here. Maybe I will. Hold on. So as we were saying, on the back of your packet, you've got a chart on the back that shows solubility graphs, and this is what they look like. Flip away. So on the bottom part of your graph, you've got temperature going across the bottom, and then you got the solubility, which is in grams per 100 grams of water. So in other words, it's a certain amount that you can dissolve into a certain amount of water. So all of these are going up except for salt, which kind of goes straight across. It doesn't change. You can only dissolve so much into every 100 grams of water. And this yttrium sulfate, which is or ytterbium sulfate, which is kind of strange in that its temperature is so big, the molecule is so big that it's actually, the faster the molecules are moving in the water, the less it's going to dissolve. But this is how you read the graph. So let's say at 50 degrees. At 50 degrees right there. Now, water, how much can you dissolve into a particular amount of water? Okay, so at 50 degrees right here, you're trying to find a certain amount of, how much any one of these will dissolve in water. Okay, so this, you would find the solubility, using this curve, you'd find the solubility of potassium nitrate, say, which would be this big curvy one here. Okay, it's purple on here, but you don't have color on yours. So you go, find the 50 degrees temperature, and well, that's where it marks out on the graph, so it looks like it's about 75, maybe, grams for every 100 grams of water, is how you'd read one of these solubility curves. That make sense? So in every 100 grams of water, you would be able to dissolve 75 grams of potassium nitrate if the water was at 50 degrees Celsius. That make sense? Okay, now, if we were to increase the temperature of the water, what would happen to the amount that we could dissolve? It would increase. It would go along this curve. So at 60, all of a sudden we're up here at 100 grams. Yeah? Okay, so that's how we read the curves. In fact, we're going to do there's an assignment in your packet that has to do with that. Okay. So, now we have the effects of pressure on solubility. Pressure itself doesn't affect solubility in most solutions, particularly unless it's a gas dissolved in a liquid. Okay, and you can think of it like this. If you increase the pressure, then you're kind of jamming the gas inside into the solution. All right, or if you lower the pressure, then you're allowing the gas, you're like kind of pulling it out because the gas is going to want to equalize the pressure inside the solution and outside the solution. Okay, so the solubility of a gas increases as the pressure of a gas is increased over the solution. Okay, which again kind of makes sense that, you know, think about your hot water bottle or your hot soda in the back of your car. You know, when it's hot out there, you're increasing the pressure on the outside. When you increase the temperature on something, you increase the pressure. So the gas, the pressure of the gas above the soda inside the bottle is going to increase, and it's jamming that gas inside. As soon as you release the pressure above the water, it's going to return to its original solubility, and all this gas is going to start shooting out. And that's why it shoots out of the top of the bottle. Okay, now this is going to bring us to the lab that we're going to do. Maybe we'll do it Monday. Okay, are the factors affecting the rate of dissolving? So, the rate at which a substance dissolves in a solution depends on three factors. The first one is the surface area of the particle. As the particle gets smaller, as particle size gets smaller, surface area increases. Okay, the more the outsides of the particles can touch its surrounding. The interaction between the solute and solvent then increases with greater surface contact. Okay, smaller particles will dissolve faster than larger ones. You guys ever seen that sugar in the raw, or it's the brown, like the plain brown wrapper sugar package that you can put your tea in, and how it takes forever to dissolve into whatever? All right, well, it does. Okay, and if you take that versus, say, granulated sugar, the granulated sugar will dissolve much, much faster because the particle size is about, you know, a quarter of that of the sugar in the raw, and so it just it dissolves faster because there's more solvent that can touch the solute and get the pieces to come up. Okay, then B, stirring increases. This is, you know, think about your iced tea again. You put your sugar into your iced tea and you start stirring it. Okay, if you let it sit there, okay, the sugar's never going to dissolve, or it'll take a long time to do it. If you stir it, you'll get more solvent touching, you'll get more interaction between the particles of the solvent and the solvent. Okay, but again, what happens if you stir or you shake a can of soda? What happens when you have to dissolve in there? Yeah, it'll spew out again. So stirring works for solid solutes in a solvent, but not so much for gases. Gases that'll actually make them come out. And then temperature. Okay, the increased kinetic energy of the particles increases the interaction between the solute and solvent. Okay, so the result is when the solvent particles move faster, a substance will dissolve more quickly. But again, what about soda? Okay, so again, this is primarily with solids dissolved in liquids. Okay, what I want you guys to do right now, and we're going to pause this, is how does all of this relate to the KMT, the kinetic molecular theory that we've had before? Remember the matter dance? We're all moving around and particles bumping into each other. How do you think dissolving is accounted for with the kinetic molecular theory? And so that's what I want you guys to write over here on the side. Okay. Moving on from there, we have saturation. Okay, this is a difficult concept, or it has proven to be difficult in the past. The idea of saturation is when you have a solution that contains as much solute as can possibly be dissolved at the existing conditions. In other words, you have dissolved at the maximum solubility level. Well, according to that picture up earlier, we saw that at 50 degrees, we can dissolve 75 grams of potassium nitrate into 100 grams of water, right? That was the point that we chose on the graph. Okay. At that point, that is the maximum amount of potassium nitrate we can dissolve into the water. That is a saturated solution. That is the saturation point, when we max out on our solubility for that particular substance. Okay? Can we dissolve 30 grams of potassium nitrate at 50 degrees Celsius? Sure. Anywhere less than that curve is fine. But that curve is the maximum amount. That's the most we can dissolve at that particular point. So, that is our saturation. Now, an unsaturated solution is when we have less than that amount. There can still be some dissolved, but it's not as much as that maximum amount. That is the unsaturated solution. It contains less than the maximum amount of solute that can be dissolved at specified conditions of temperature and pressure. Which brings us to the more confusing one, which is a supersaturated solution, which I'm sure sounds great on the recording. Supersaturated solution. All right. So think about what happens here. We take our 50-degree water. We dissolve 75 grams of potassium nitrate into that stuff. Then we let the water cool down. What do you think is, if we let the water cool down, there should be less potassium nitrate that's going to stay dissolved in the water, right? But what often happens is as you let the water cool down, that same amount stays dissolved in the water. Which means that there's a greater amount of dissolved solute than what should be there if it was saturated. Does that make sense? That there's actually more than what it should be capable of holding. Okay, and this generally only occurs when you heat up a solvent, dissolve up to solubility, and then let it cool again, and then you're going to get this extra amount of solute dissolved in the solution. Okay, the lab we're going to do, or this graphics, the interpreting graphics that's in your packet, involves the supersaturated stuff. What does it look like if you have What does it look like then if you have, if all this stuff comes out? What do you have at the bottom of the solution then? Yeah, we've got the solute in there. We've got the solute that didn't have a chance to dissolve. Okay, so a supersaturated solution will actually have more than enough, and if that stuff were actually to come out, if it were to reestablish itself, then you'd have a whole bunch of solute at the not dissolved at the bottom of your solution. Okay, so supersaturated has more than. Okay, a supersaturated solution has more than what you expect from just filling up its solubility. Okay, moving on. Next page. Supersaturated solutions that are made by, or we just said this, dissolving excess solute at higher temperatures. We just talked about that. For example, you guys have ever made rock candy? You guys made rock candy before? No. No? Some of you had the opportunity to do it. I wish we could do it in here, but the materials we have aren't sterile.
What if we bring
So, nah.
Why not?
I try. It tries too hard. It's too difficult to do. It took too long. I tried to do it last year, and it didn't. It just totally didn't work. So because it took too long.
What do you need to do?
All right. What do you need to do? Okay. Well, the idea behind rock candy, is that you heat up water and you dissolve a whole lot of sugar into the water, and then pour it out into a cup or a glass or something, and then put like a string into it, which will give it like a place to. It's called a nucleation site. It's where the crystal will start to form, and as the temperature of your liquid cools, it will the sugar will start to form crystals, and the supersaturated, the extra saturated stuff, the extra sugar that's in the solution, will start to leave the solution and form a crystal inside. Inside of your solvent.
Water and sugar.
Sugar and water, and if you want to put some flavoring in there. You can find flavorings. What's that? We'll try. We're gonna do a different. This is the tough lab to do. But we're gonna have a different one. It's not gonna be the supersaturated lab.
Have you done it before?
I've never successfully done it. That's the other reason why. Okay. Sorry. Labs are no fun if they don't work. Okay, which brings us to concentration. We actually have a way of measuring. Actually, no, I'm going to stop here.